Hello everyone, thank you so much for joining us today. My name is Victoria Getz and I'm a Senior Marketing Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled Developing an SCR Structural Digital Twin Using Machine Learning. Before we get started, I would like to cover a few important housekeeping items. This webinar will be 30 minutes of presentation followed by up to 15 minutes of Q&A. This webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I am very happy to introduce our speaker today, Shankar Sudaraman. Shankar is a principal engineer at 2H Offshore in Houston. He has 15 years of engineering and research experience in structural dynamics and vibration analysis. He has been working in the oil and gas industry since 2007, including riser analysis and drilling mechanics research. Shankar holds a PhD degree in mechanical engineering from Purdue University and is a PE in the state of Texas. So now I will turn things over to Shankar to get us started.
Thank you, Victoria, for the warm introduction. I'm excited to be here today to speak on this topic and hope you'll all find the information useful. Today's presentation is on SCR Digital Twin. Through this presentation, we will describe an SCR Digital Twin that is developed using machine learning models. A second learning objective is to gain a better understanding of how advanced analytics, including machine learning, can provide a high-fidelity load, stress, and fatigue tracker. This in turn provides a more accurate information for life extension assessment. The inputs to this model include environmental, operational, inspection, and monitoring data, and we will show you how all the info is utilized in the development of suitable models for relevant applications. To address these learning objectives, we will first start off with a brief introduction, follow up with the analytics workflow for riser assessment, and demonstrate using two SCR touchdown zone assessment case studies, and finally close with a summary. In the typical offshore monitoring condition, the norm is to monitor vessel motions and some form of environmental monitoring. Direct structural monitoring is seldom carried out, in part because of cost and deployment issues. Furthermore, even if all this information is available, analysis is carried out with a reduced set of sea states, for it's not feasible to run hundreds of hours of FEA simulations using measured vessel motions. So what then is the alternative? The machine learning solution is to predict riser response at critical locations along the riser, essentially behaving as a form of virtual strain gauge. The best part of this solution is it can be calibrated using any available riser structural monitoring system already deployed in the field. That's what is demonstrated through this flow diagram that shows a predicted response through this virtual structural digital twin. Let's now look at a typical production riser in the form of a lazy wave. The primary loads include current, wave, and vessel offsets. This is in the form of direct environmental loading on the riser system. Additionally, we have loading through the vessel in the form of 6 degrees of freedom motions as a response to these environmental loads. The critical areas include the riser hangoff, which can be in the form of a flex joint, a tapered stress joint, or a clamp, the bottom of the sag bend, the top of the hog bend, and the touchdown zone. The touchdown zone critical point might be a singular touchdown point, but is most often spread over a region. These represent the hotspots that we had referred to earlier. The input data is often the 6th degree of freedom vessel motion and can be in the form of a combination of first and second order motion combined with GPS position data. Implicitly, direct environmental loading is included, as we just discussed. The response at these multiple locations can then be examined, specifically the two-plane bending moment and the effective tension. Now that we have laid out critical locations of interest, we'll now talk about what applications we can use these in. We can monitor dynamic structures for short-term operational decision support. For example, a post-hurricane or severe current event startup. This approach can also be used for long-term integrity management, wherein we can use real-time fatigue damage tracking. An example is calculation of corrosion fatigue, or this can be for severe mid-ocean conditions. For example, beam sea load conditions are often more severe than head sea conditions. The primary advantage of such a virtual system is in the cost for deployment. It uses existing infrastructure for life of platform monitoring. The other advantage is that by this type of monitoring, we can perform life extension assessment for all risers in an asset. A digital twin system must also eliminate lengthy computation analysis time while also reducing conservative assumptions from design. We talked about the what and the why. Now we will discuss about how we can implement this. To do this, we need a trained algorithm. Training is based on input vessel motion data and target load and stress time traces at key locations of interest. This is accomplished using a subset of physics-based FEA simulations and monitor data. As a result, you get an output response that is functionally dependent on the past history. The trained model needs to be validated for deployment. During this phase, you have access to both original data and the machine learning algorithm. We feed C-state data in multiple directions to the machine learning model to generate load and stress time traces. From this, we estimate, for instance, fatigue damage and assess it against some form of key performance indicators for integrity management applications. This is the predictive analytics that we talked about. To elaborate on this, a portion of this data is used for training and the other portion is used for cross-validation. Aim is to identify a good enough algorithm that best represents the physics-based FEA model. Once a trained model is available, we can deploy the algorithm either on the edge or on the cloud. The algorithm deployed can be used either in an edge or cloud-based app infrastructure that actively tracks the life. We will now start with the first of two case studies to talk further about this approach. As we stated previously, the purpose here is to demonstrate the riser structural twin. We are showing this development in two stages. The first model uses design sea states and attempts to predict other design sea states at a challenging hotspot location, the riser touchdown zone location. In this example, we are considering a riser deployed from a deep draft semi at a water depth of 4,000 feet. The significant wave heights are between 1.5 to 45 feet with peak periods between 3.5 and 18 seconds. These environmental loads are in multiple directions with a total of 188 sea states shown for this assessment. Again, the objective is to obtain a single algorithm that relates the 6 degree of freedom motion for all these sea states at this touchdown zone location. Now that we talked about the objective, we'll look into the initial set of correlations. What if the linear relationships have insight into what exactly drives the response characteristics? Looking at the 6 degree of freedom vessel motions, that's what we are looking at in terms of the x-axis information here. We look at the three loads, the two plane bending moments and the effective tension. You can see that the scatter diagram is kind of dispersed, indicating that the input-output directly are poorly correlated. This is because the information is deeply embedded in the response characteristics. And to glean that, we need a machine learning model to actually extract that information. So, the machine learning model that we will be using is the convolutional neural network, and this model is typically used for image recognition. It has a standard flow diagram with a set of convolutional layers which basically enhance the accuracy of the response that you get from the model. In here, it requires intensive computational effort and is typically used for complex data sets. And this resulting high accuracy ensures that you basically have a well-developed machine learning model. This requires up to 50% of the sea state vessel motion time traces and for training, and the remaining then can be used for validation. This training is feasible either on the edge or in the cloud, and all of these are estimated based on an accuracy of estimation which relates the fatigue damage that you predict using machine learning with the fatigue damage that you obtain using FEA. So the first step is once we pass the information through the model, we basically obtain a range of different sea states and we compare the FEA time trace with the machine learning predicted time trace. What you can see for the two plane bending moments is that the machine learning model performs pretty well for a range of these different sea states, whether they be transverse, far, or near. Once we have that, then we can basically compute stress time traces and then obtain fatigue damage results comparing both the FEA and the basically the measured predicted machine learning sea states. From this, you can see that the machine learning model does a good job of tracking all these low and high sea states for far, near, and across. On this bottom chart, we see the percentage difference in fatigue damage prediction between machine learning and FEA. And what we see here is that less than 30% accuracy for all 3R sea states are seen. And for a good majority of them, which is basically 94% of the 3R sea states, you have an inaccuracy of less than 20%. This represents a high fidelity designed machine learning model. This can further be emphasized by looking at the predicted fatigue damage rate on the y-axis and the target fatigue damage rate on the x-axis, and looking at the level of prediction. Remember, previously we had shown a scatter diagram which was kind of dispersed. So what we see here is that all of these now lie on this straight line, and that's basically the beauty of this machine learning model. What we have here is that a majority of these high C states, and zooming in further, the medium fatigue damage C states are within 15%. The probability scale fatigue damage difference is within 6%. All this means that you have a high fidelity machine learning model. That's the case study one, wherein we looked at design C states and we looked at other design C states for the cross validation, which is what is indicated here, to basically prove the point that we can actually do this for the design model. In the next case study, we basically are looking into developing a machine learning model using design C states and then cross-validating both against initially with the design C states and then representatively using the measured C states. In here, the objective is to show what we can do when we have measured C states. Here, we have a spar at a water depth of approximately 4,000 feet and a similar set of environmental conditions to the last case study. Again, we have multiple directions and multiple C states with first and second order motions. The measured environmental data have similar kind of characteristics and again with full 360 degree of wave directions. Herein, just as before, we do the training with the design C states, and then for the primary cross validation, we use measure data to pass the model for suitable predictive analytics. Let's look first at the design C states, the characteristic of these C states. We have surge on the x-axis and sway on the y-axis just to indicate the range of motion that you have for all these different C states. During the training process, we consider low C states, medium C states, and high C states in different directions, including near, across, and far. This machine learning training is therefore accomplished using a range of these just to ensure that you cover all the positions that the spar may occupy. Once that's done, we parse through the machine learning model, obtain the time traces, and then obtain stress time traces, and onward to the fatigue damage rate prediction, similar to the previous example. What you see is the predicted damage rate on the y-axis and the target fatigue damage rate on the x-axis. As before, a majority of these high and medium C states are all within 15%. This indicates that the machine learning algorithm that we have developed tracks the overall trend well. This indicates also that we have a single machine learning model that basically encompasses the range of C states and directions that we are deployed. The distinction between the previous example and this one is that here we now feed in the measured input motions, wherein the characteristic of the measured input motions is shown on the left-hand side graph. This measured muscle motion is passed through the FEA model, and we obtain the FEA structural response at the touchdown point location of interest. This represents our target C state. The measured vessel motions is also then passed through the machine learning algorithm, which was previously trained with the design C states, and now we have a predicted response obtained from the machine learning model. This represents the virtual riser twin. This is what we will be cross-validating for these blind measured C states. Over the next few slides, I'll show a range of different time traces just to show how the degree of match. Herein, we first look at storm A. we look at about 10 storms as an example out here. We have on this particular chart the fatigue damage rate of the target and the predicted, which is shown in bar charts, and then the line showing the level of inaccuracy. So one of the things that you notice also here is these time traces. The time traces on top represent the out of plane bending moment. The middle set of time traces represent the in plane bending moment, and the bottom time traces represent the effective tension. Looking at the storm A results, the bending moment X maximum prediction inaccuracy is 25%, while that of the out of plane bending moment, in plane bending moment, and the effective tension is less than 10%. The resulting fatigue damage difference is less than 20% overall. Looking at a second storm, storm F, we basically see a similar kind of response, and the only distinction is in the out of plane bending moment, and even here the first order response is captured pretty well. Considering all this, the measured fatigue damage rate is a slightly higher 30% inaccuracy, but this still represents a pretty good match. A third storm, which is storm I, we basically see a measured fatigue damage difference of less than 15%, and again here the first order track is maintained, and while you basically see quite a bit of non-stationarity overall in the actual response characteristic. That basically shows what happened in the two case studies, and we have demonstrated what the level of efficacy of the machine learning model. Once this trained algorithm is available, we can process 1 day of data within 1 minute. This allows for deployment on edge-based or cloud-based infrastructure, providing near real-time response. We can obtain real-time stress, load, and fatigue trackers, obtain accumulated fatigue damage, and remnant fatigue life info. Machine learning algorithms and riser digital twins can then be integrated with existing IT infrastructure on board the rig and allows for communication with data center. Thereby, real-time analytics and multiple pipelines can be obtained for generating suitable apps for maintenance and operations. In conclusion, we have demonstrated through two case studies the proof of concept development of SCR digital twins at a challenging touchdown zone location. The fatigue damage prediction accuracy is within 20% for all sea states with one algorithm, including blind cross-validation sea states. Once a trained algorithm is obtained, this allows for high-speed processing with 1 day of vessel motion that can be processed in 1 minute. This allows for real-time operational guidance with large cost savings in comparison to conventional riser monitoring systems. We can use machine learning for monitoring dynamic structures at key locations that can provide both short-term operational decision support and long-term integrity management through fatigue damage tracking. This allows us to digitalize subsea and automate processes for increased efficiency and throughput. This concludes today's webinar. We thank you all for joining us to learn more about the SCR digital twin. At this time, I will hand it back to Victoria for the Q&A portion of this session.
Thank you, Shankar. We've already had some great questions from our audience, so I will go ahead and get started asking those. And in the meantime, if you have any more questions, feel free to drop them in the Q&A box on the right-hand side of your screen while we are in the middle of this Q&A. Okay, the first question. It takes 24 hours to process 1 minute of data. But how long does it take to train a model?
This is a
Does
great question.
longer training,
The
i.e. months,
preliminary
improve
model
response
training
prediction?
can take between 1 to 2 weeks and can be done concurrently with any design analysis work. An improved response can be obtained through longer training. This includes appropriate feature selection and algorithm usage. Yes, definitely, a longer training will improve response prediction.
Okay, the second question. Can you
Yes.
predict extreme rise
In both
response
case
using the
studies
machine
that we
learning
have
model that you
assessed,
trained using
response
regular
outside the
C-states?
domain of the training, and the algorithm performs robustly. Yes, there is a marginal reduction in accuracy, but this is within acceptable limits. We have used data from a C-state
Okay,
scatter
the next
diagram that
question.
was
What data
provided
has been
from
used for
a
this
Metocean
training?
report for all the design C-states that were used for the training.
Okay, next
This is an
question. How
excellent
do you
question.
prevent model
So to
overfitting?
prevent model overfitting, we have built-in extra selections to basically ensure that the model will be robust to a range of different characteristics. One of the things that we do is we split it into training C states and cross-validation C states. These cross-validation C states are time traces that the machine learning model does not see during training. Then we then check all these through this cross-validation C states to ensure that all of these are within the same accuracy band. This is a very good question. Measure data cleaning is one of the
Okay, how do you
most
do measured
important
data
steps
cleaning?
that you have to undertake. This is typically done using a sequence of filters and appropriate statistics to just eliminate their bad data. We have notions of what typically would represent a good data set, and then once we have that clean data set, we will then parse it through the machine learning model.
Okay, the next question. If we already have an FEA model, why do we bother to
I
train a
agree.
neutral network to
Machine
replicate the
learning
same
does
result
not
with
replace
certain
the
errors?
FEA work.
What
The
benefits can we get
purpose
from
here
machine
is more
learning?
focused towards hotspot, load, stress, and fatigue real-time tracking. Essentially, the benefit is that we can use this near real time and life of platform integrity management using measure data, not merely a set of reduced C states. As I mentioned, we can process 24 hours of data in literally a minute. So that's where you glean all your benefits.
Okay, what effort is needed to improve the numerical models? The accuracy can be improved if the numerical FEA is closer to
Yes,
reality, or
the
can
accuracy
it?
can be improved if the numerical FEA is definitely closer to reality. There's, for instance, it could be the hydrodynamic coefficients that you're using or the model itself. In addition, the machine learning model requires other knobs that you need to tweak. And as I mentioned previously, a longer training will typically help improve the response characteristic. Yes,
How is the
I
machine
agree.
learning
The machine
approach better
learning
than
does
FEA
not replace the
predictions? I
FEA
can get
work.
more
This
accurate
is
results using
similar to
FEA.
the question that I'd previously addressed. So what it is we basically use it for near real-time tracking as well as life of platform integrity management. So that's primarily the benefit where we can see machine learning coming in.
Is there any actual stress measurement needed at the TDP of the SCR for the learning model?
Uh, Ideally, yes, but we typically do not get any of these measurements. The majority of your deployments offshore are not instrumented. So if we had a stress response that would enable us to improve our overall capabilities for prediction, whether through FEA or through machine learning. That's a good question. So digital
Where
twins
else do you
are
see
more
this digital
broad. It's
twin being
basically we
used?
can while we talked here primarily about SCRs, it can be applied for any type of risers. It could be drilling riser and wellhead applications. It could be for flexible risers. It could be for uh, uh, conductor supported platforms. It could also be for mooring lines and tendons. So this can encompass any portion of a subsea asset that we can probably have deployed offshore. In addition, this is a generic term for all systems. So any structural system that can be represented by a certain set of inputs and a certain set of outputs can be represented through a digital twin. That's a good question. So
How do you
one of the
reconcile
important parts
simulated data
is
with
what
real
we
data
see
in the
as the
machine learning
input
model?
data. The input data for the FEA model as well as the ones that you actually obtain for the measure data need to be identical. If not, it needs to be modified so that it is as identical as possible. Once you have that, you have to use suitable data cleaning. That way, we basically ensure we have a robust enough time trace as input information before you parse it through any of these machine learning models. That's how we reconcile it.
For time series data,
This
why don't
again
we
is a
use
good question.
recurrent
We
neutral
use both
network like
LSTMs as well
LSTM
as
instead of
CNN. In this
CNN?
particular example, we actually have been using, uh, prefer to use CNN because of the complexity of the data. Once data becomes more complex, including recurrent neural network becomes a little bit more challenging. So adopting CNN has given us much better results. No, we
Does your
don't
model
account
account for
for
fatigue
fatigue
damage due
damage
to
due to
VIV
VIV
loads?
loads.
Are the VIV loads
Uh,
included in the
so uh,
training?
while current information is included as part of the input environmental loading that the model originally sees, this is not included as part of the training here. Especially a lot of the production risers typically have some level of uh, VIV suppression devices. So that's how we basically pass through it.
Being not familiar with the norms of
This is an
prediction
excellent
accuracy,
question.
what percentage prediction accuracy
Ideally,
do you
we would
consider
like a
high fidelity?
100% match with 0% loss in prediction accuracy as a high fidelity match. Since we are dealing with complex dynamic systems, this gets reduced in part when we deal with fatigue damage estimation, this is further reduced by the fatigue exponent. A prediction accuracy loss of 5% in the stress time trace implies a reduced accuracy of 15 to 20% in fatigue damage. Based on our typical expectations, a maximum inaccuracy of 20% for design C states and 5% for the probability scale damage C states will represent a high fidelity prediction. Yes, we have developed
Okay,
a
and I think
machine
our
learning
last
twin
question is
for
about
one of our
track record.
clients in a
Has this been
real
employed in a real offshore
installation.
installation yet? Well, thank you, Shankar, for all the information on the topic. I think we've answered all the questions that we had, and that is all the time we have for today. But as we mentioned earlier, if we didn't get to your question or you think of something after the webinar ends, or if you'd like to continue the discussion, please contact Shankar directly using the details provided here. Thank you to our audience for your time and participation, and we hope you all found this useful and will join us for more webinars later this year covering a range of riser and subsea topics. Again, please look out for the recording of the webinar